the distance is minimized. Okay, so I want to take U and project it onto a subspace V. That means I want to pick a vector V in V such that this distance is minimum, right? So what should I do? Infimum or all V in V, right? Okay. Well, this infimum will give me the projection, right? In fact, it will give me the projection length, right? So essentially, if you have this and this is your V, it gives me this length. It doesn't give me what is the vector. So of course I do arg. This gives me a vector V star in V, that is the projection of U onto V. Okay, so is that fine? We will see why this is the case later on. It has got something to do with this vector also. Okay, right? This matrix. Okay, I can write the solution as PV times U will give me V star. So essentially, I should be able to write this as PV V star. Sorry, PV U. So, okay, fine. Anyway, keep this in mind. Okay, so let's move on. Few things. So let's look at this. Let X be a R cross N cross N matrix. Okay. Let norm of X be less than 1. This norm is basically sup norm. Okay, you know what sup norm is, right? You know what sup norm is? It's basically what is it called? Huh? Sup norm is what? What is sup norm? What is sup norm? It's AX or norm of AX or norm of X. Take maximization over all X, right? That gives me the sup norm. Okay. Let's also add and let me make it symmetric also for some reason. Okay. Then what can you say about I minus X? Okay, I'll leave it as a blank here. Okay. Let's see what can you say about this unit matrix. Okay. Is it invertible, I minus X? Is it invertible? How do you verify that? Suppose the moment you see this, right? So what can you say about the matrix? X is equal to X transpose, symmetric. The moment you see symmetric matrix, what do you infer? What do you infer? Huh? Huh? Louder. Eigen? Yeah, it has eigenvalue decomposition, right? So the moment you have eigenvalue decomposition, so now I want this I minus X, I want to talk about the invertibility of this matrix. So what is it that I have to answer? Suppose I say the eigenvalue of X is not 1, then definitely this is invertible, right? Do you agree? Suppose, okay, so let me write this. Suppose the eigenvalues of X is not equal to 1, then let's see what happens. So I minus, I can write it as U lambda U transpose. So this I can write it as U I minus lambda U transpose, because U transpose is identity, right? So I can write this. Now, what do you think is the inverse? I take U I minus lambda U transpose. What do you think is the inverse of this? First, I'll multiply by U transpose. Okay, I'll do that to the other side. Maybe I'll use different color. I'll multiply by U transpose U will give me identity, right? I'll have I minus lambda. I have to cancel that. I have to do I minus lambda inverse. When can I do I minus lambda inverse? Remember, lambda is diagonal, I is diagonal, so the difference is diagonal. So when can you invert a diagonal matrix? When the diagonal entries are non-zero, right? When will it be non-zero? If the eigenvalues of this is not equal to 1, right? Then, of course, what is the eigenvalue of an identity matrix? it has all the eigenvalues equal to 1, right? So 1 minus something that's not equal to 1 will never be 0. So it's invertible, right? That's why we need this times U transpose. What do you think is the answer? This is identity, right? Right? Similarly, if I multiply, so let me call this as X inverse. Okay, it's a symmetric matrix, right? X inverse is also symmetric, right? So I could come up with inverse of X when the eigenvalues of X is not equal to 1, right? Let's see when does this happen. Okay, so when we need to check this, right? So we need to check this, right? Let's see how to check this. Okay. Okay. So now suppose suppose I say that the eigenvalue is 1 for this. Suppose this is not true, but suppose this is true, right? That means if I take norm on both sides, it will be equal to V itself. Do you agree? Assume V is a unit vector. So this implies norm of xv equal to norm of V. So what can you say about, can you say something else for this? How do you prove that this has inverse? What do you think is the answer? Now I have to somehow prove that the eigenvalues are not equal to 1. So how do you prove that the eigenvalue is not equal to 1? Huh? Any idea? So this implies, let's see, 1 equal to norm of x v divided by norm of v, right? Do you agree? Is that fine? Okay. Now 1. So if I, instead of choosing any v, I'll choose the v that maximizes this ratio, right? So that means I'm going to try to maximize the right hand side. Then it should be more than 1. 1 should be less than or equal to, right? Supremum over all v norm of xv over norm of v, right? But what can you say about this? This is what? This is norm of x, right? So norm of x is definitely greater than 1, right? Sorry, what did I assume? Yeah, it's less than 1, right? But it's less than 1, right? So what is the contradiction now? So we arrived with the contradiction, right? Do you agree with this? We started by saying, well, the eigenvalue is 1, and then we went ahead, but it led to something like norm of x is less than 1, but it's greater than or equal to 1. That's what we have. But the assumption was it was less than 1. Contradiction, right? This implies what? The max eigenvalue, the eigenvalue can never be equal to 1, right? Right? Okay, so this implies lambda I not equal to 1 for all I, right? So it doesn't matter which eigenvalue. Okay, so therefore I minus x is invertible. Okay, so before moving into one important thing called singular value decomposition, I want to do something analogous to what you do in your simple calculus. Suppose I have this. Okay, this is what 1 minus x, the inverse, that is 1 over 1 minus x, right? It has a Taylor series expansion, right? So what is the expansion here? Can somebody tell me? Huh? 1 minus x plus factorial plus minus, this is your, right? Do you agree?